This is the 12th lecture on natural response of electrical circuits. We have already defined the various kinds of responses that an electrical circuit can have, and we have said that natural response is the one which arises due to internal stored energies and the circuit being left to itself to settle. There are no external forces or external excitations. If there are external excitations, then the response that we get is called the forced response. And in general, a circuit may have excitations, voltage sources or current sources or both, and also internally stored energies like electrostatic energy in capacitors and electromagnetic energy in inductors, and therefore in general the response of an electrical circuit shall be a combination of natural response and forced response. And then two other terms which we introduced were the transient response, that is the response that occurs at the beginning of excitation, and after a long time has passed, the response that you get from an electrical circuit is called the steady state response. So there are four kinds of responses: natural, forced, transient and steady state. Sometimes natural response and transient response are wrongly identified with each other. They are not necessarily the same. Similarly, forced response and the steady state response are also not necessarily the same. The previous day I had also introduced to you terms like order of a circuit, and we said that a first order circuit is one which has effectively one energy storage element, that is either one inductor or one capacitor. All right, there may be more than one capacitors or there may be more than one inductors trivially connected to each other, which behave as a single energy storage element. And one of the examples that I gave was something like this. If you have, let's say, three capacitors like this and there is a resistance here, then you know these three capacitors behave like a single capacitor. It would be C1 plus C2 C3 divided by C2 plus C3, and therefore this is the effective capacitance connected across the resistance R, and this behaves as a first order circuit with an effective time constant of this total effective capacitance multiplied by the effective resistance across it. Similarly, there may be more than one resistor here, but effectively they behave like one resistor. Similarly, we can have a resistance inductance circuit which will also be a first order circuit, or a multiplicity of inductors connected in a trivial manner so that they could be reduced to one effective inductance, then that is also a first order circuit. And as an example, I had taken this circuit. Let's say we have a battery V and a resistance R which is connected to, let's say, an inductor L in series with a resistance R. All right, the switch is left in this position for a very long time, so that the current that passes to this circuit would be given by V by R1 plus R. The inductance is not effective in dropping a voltage when the current is steady. So in the steady state, the current in the circuit shall be given by V by R1 plus R, and let's call this as I0. At t equal to 0, this switch there is a connection here. At t equal to 0, this switch is moved in the downward direction. Alright, this is how we indicate this. At t equal to 0, this switch is moved to the downward position, so that the initial current in the inductor was carrying a current of I0. Now the inductor and the resistor in series, they are connected across a short circuit, and therefore this circuit will have a natural response. It is an example of a first order circuit having a natural response. That is, we are interested in the behavior of the circuit at t greater than 0. The initial condition is that if I consider this current as I, then I of 0 minus, that is just before the switch is closed, is equal to I0. I of 0 minus just before the switch is thrown in the other position, I of 0 minus, this is the indication, this is the significance of the minus sign here, is I0, and you know the energy of an inductor cannot change instantaneously, and therefore this will be I of 0 plus also. Alright, and you can see that as time passes, the inductor shall lose its energy to the resistor. The resistor will dissipate that energy, and gradually this current should diminish with time, and at infinity, at time t equal to infinity, the current should diminish to 0. The differential equation that one can write is simply application of KVL, that the drop across the inductance plus the drop across the resistance should be equal to 0, because there is a short circuit, and therefore the drop across the inductance is L di dt, the drop across the resistance is Ri, and this should be equal to 0. This is a first order differential equation, and this is what defines the order of a circuit. If a circuit natural response can be described by a first order differential equation, then it is a first order circuit. This is not the only one. We could have a capacitor resistor circuit, for example. Let's say we have a battery V 0 connected like this, connected across a capacitor C, and then there is a resistor waiting to receive energy from the capacitor C. This is the capacitor C, and then we know that if this switch is left in this position for a long time, then the capacitor voltage V sub C, if we call this V sub C with this polarity, the capacitor voltage V sub C at 0 minus shall be equal to V0. It will assume the voltage of the battery, and if this switch is thrown to the other position at t equal to 0, then the capacitor, which has stored energy, will now try to send a current through R. Let this current be I. Alright, it will try to send a current through R, and in the process the capacitor will discharge, or it will lose its energy. Gradually this energy will be lost in the resistance as heat dissipation, and gradually as time increases the current will decrease, the voltage across the capacitor will decrease, and it will take infinite amount of time for the capacitor to completely relax, that is completely lose the energy that it has contained. And once again, since a capacitor cannot change its energy instantaneously, the voltage across the capacitor at 0 plus shall also be equal to V0. And if you see the differential equation, if you see the equation describing this, once again it is an application of KVL or common sense. Alright, it says that if the current IR, the drop across the resistance IR, should be equal to the drop across the capacitor, that is V sub C. Now what is V sub C? V sub C had started with V0 at t equal to 0, and as time proceeds, this current I, it is important to understand this current I has to flow in a closed circuit, and therefore this current I charges the capacitor in the opposite direction, which is equivalent to saying that the capacitor is losing charge. What is this charge? It is equal to 1 by C times the charge, integral 0 to t I dt. This is the equation. Is this equation clear? The charge, the voltage across the capacitor at any instant of time would be the initial voltage minus the voltage that it would have acquired in the opposite direction because of the current I flowing in a closed loop. Now, this is not a differential equation, it is an integral equation. In general we may get an integro differential equation. In the previous case, in the LR case, it was a differential equation, pure differential equation. In the RC case, it is a pure integral equation. Nevertheless, one can make it into a differential equation by one more differentiation, R di dt plus I by C. If you differentiate this, it's simply I over C. That would be equal to dV0 dt is 0. So this is also as you can see a first order differential equation, and therefore this circuit is also a first order circuit. Let's see what kind of solution you get. You are acquainted with the solution to such differential equations, but in the context of electrical circuits we wish to bring in some more physical concepts, and I want you to pay attention to this. Let's take the second circuit first, where our differential equation was R di dt plus I by C equal to 0. Now the right hand side of this equation is 0, which means that this is a homogeneous differential equation, homogeneous differential. There is no forcing term. Well, there cannot be a forcing term because we are investigating natural response. It's quite logical that our right hand side is 0, that this is a homogeneous differential equation of the first order homogeneous differential equation. Now in order to solve this equation, we know mechanically how we do it. You put an integrating factor and things like that, or you take the this quantity to the right hand side and integrate, change of variables and so on. You know all this. We shall do it in a slightly different manner, which is more physical in character, which throws more light into the physical happening in the circuit. We argue that any solution to this differential equation has to satisfy this di dt equal to minus I by C. Any solution has to satisfy this, which means that di dt shall be equal to minus 1 by RC times I. Alright. So what you usually do is bring I here, di by I minus 1 by RC dt, then you integrate both sides and so on. But no, we are not going to do that. What we are going to argue is, now comes the physical picture into the situation. What we argue is that my solution must be of a form such that di dt cancels I by C, or di dt and minus I by RC must be identical, and a function which eminently qualifies for this kind of a job is the exponential function. You know that the exponential function, the differential coefficient, is again an exponential function, and therefore you argue that it must be of the form e to the power some constant s, small s, times t. Time has to be there. Time is the independent variable. It's an exponential function of time. It could be a constant multiplied by time. And then we argue that in general the solution must be of this form, some arbitrary constant multiplied by e to the st. So is this physical reasoning clear? That the solution must be of this form, a e to the st. A is an arbitrary constant which will be determined by the initial conditions or the boundary conditions of the problem. Exponential function we took because di dt, ddt of this must be of the same form as I, same form as the function, and therefore it must be an exponential function. Now if I substitute this in the original equation, then what I get is, our original equation is R di dt plus I by C equal to 0, and I substitute I equal to a e to the st This is called a trial solution. We try a solution of this form, then I get R A S e to the st plus A by C e to the st equal to 0, where A e to the st cannot be equal to 0, because this is the form of the solution. If this is 0, then of course the current is identically equal to 0. Current identical equal to 0 obviously satisfies the equation. That cannot be a solution, because we know that if the capacitor has an initial energy, it shall send a non-zero current, and therefore I cannot be 0. Therefore A e to the st cannot be 0. The only other alternative is that R times S plus 1 by C should be equal to 0, which means that S should be equal to minus 1 over RC. Alright, S should be equal to minus 1 over RC. In other words, the solution to the equation shall be of the form A e to the power minus T divided by RC. And you notice that RC, the product RC, must have the dimensions of time, and therefore we denote this as a time constant, and we say A e to the power minus T by capital T. The only problem that remains is to find out capital A. Alright, that is found out from the initial condition. You know that if we draw this circuit again, it is a C in parallel with R, this is I, and you know that Vc 0 plus is the same as Vc 0 minus. We recall that this is equal to V0, and therefore what is I of 0 plus? It must be V0 by R. Our solution is A e to the power minus T by T. So I of 0 plus is obtained by putting T equal to 0, which means that A must be equal to V0 by R, and therefore the total solution is V0 by R e to the minus T by T. Alright. Now let us call this as I0 e to the minus T by T. Okay. Now if you plot this current versus time, if you plot this current versus time, then it starts at I0, and falls exponentially, and you know how to define the time constant, that it is the time after which the current has fallen by how much? 1 by E of its original value, and so on and so forth. The point is, the current is decaying exponentially. It is only at infinite time, small t equal to infinity, that the current shall diminish to 0. What is the charge that flows? After all, the capacitor started with a certain amount of charge which was equal to C times V0. Alright. So how much charge does the capacitor lose in the process? Alright. That obviously will be obtained by integrating this over from 0 to infinity. Now, so the charge that has passed shall be equal to I0 integral 0 to infinity e to the minus T by T dt, and it is very easy to see that this is simply equal to I0 times capital T. Okay, you integrate this and put the limits. I0 times capital T. I0 is V0 by R, and capital T is RC, and you can see that this is precisely the total charge that the capacitor loses in the process of sending a current to the resistant, is precisely the charge that it started with. So it loses its whole charge. Is that clear? This is the physical reasoning that I wanted to bring into the solution of the differential equation. You should not do it blindly, you must have the physical picture in mind. In an exactly similar manner, we can take care of the inductance resistance circuit LR, which is short circuited with the current I here, I of 0 minus equal to I of 0 plus equal to, let us say, I0. And the differential equation satisfied by the circuit is L di dt plus Ri equal to 0. If you proceed exactly similarly, that is, you put small I equal to a e to the power st. Incidentally, what should be the dimension of s? 1 by t, second to the minus 1, and 1 by t is a frequency, and therefore small s is called a frequency. We will come to this a little later, the physical interpretation of small s, and you will see how nicely it tunes with physical concepts of frequency. But if you try a solution of this form and obtain and substitute this initial condition, that is I0 equal to I0, you shall be able to show that It is exactly of the same form, that is I0 e to the power minus t by capital T, where capital T is now equal to R upon L. Instead of RC, it is R upon L. Alright, and the same kind of argument about the total charge that passes in the circuit. If you integrate this, it would be I0 times capital T. This also incidentally brings in another definition of capital T. Isn't that right? What is the definition? Another definition of capital T. One definition of time constant is the time required for the current to drop by 1 by eth of its value at t equal to 0. Another definition could be in terms of charge, that it is effectively the initial current. If the initial current had passed for a time equal to capital T, then the charge that is lost would be equal to the actual charge lost by the capacitor, or actual charge flowing in this circuit for infinite amount of time. Is that clear? Let us go back here. Pardon me? Time constant, you see, can be written as T equal to V0C divided by I0. If I go back to the original problem.
In that inductor thing, it should be T equal to L by R. Yes, sir, L by R.
Why did it take so long? Thank you. This is the correct story. All right. Now, an interpretation of the time constant. It's more evident in the capacitor resistor circuit. The capacitor started with a total charge of V0C, and you see, if it had sent a current at the rate, if it had sent a constant current I0, then it requires only a time equal to capital T to lose the whole charge. So you can define capital T as that amount of time is the time required for the capacitor to lose its charge if it maintains a constant current at the initial value. This is another interpretation or definition of the time constant. Now, enough about the first order circuit. Now, let us look at a second order circuit. Let us consider a capacitor C, which is charged to a voltage V0, all right, and then at let's say t equal to 0, this capacitor is first charged to a voltage V0, maybe by connecting a battery across this, a battery of voltage V0. It has in the circuit an inductance and a resistance and a switch. If the switch is open, then the capacitor sits pretty, it doesn't have to lose charge. But suppose the switch is closed at t equal to 0. The switch is thrown into the lower position at t equal to 0. Then obviously the capacitor cannot sit pretty, it shall have to lose charge. A current shall flow like this. Capacitor is charged with this plate positive, so this charge will effectively behave like a battery. You remember the Thevenin equivalent circuit, which will tend to send a current in this direction. And as time passes, this current I has to pass through the capacitor in the opposite direction, which means that the capacitor gets charged in the opposite direction, which is equivalent to saying that the capacitor loses charge, and as time proceeds it loses more and more charge, and therefore the current gradually diminishes, the charge diminishes, and after infinite amount of time the circuit will again be relaxed. That means it shall have no initial energy. Let us look at the equation. What kind of equation does this circuit obey? Obviously, once again it is a simple application of KVL, and you notice that the inductor voltage L di dt plus Ri, this should be equal to V sub C, but V sub C starts with V0, then discharges, that is the current charges in the opposite direction, 1 by C integral 0 to t I dt. This is the equation that is obeyed by the circuit, and you notice that this is an integro differential equation with the initial conditions that, what is the initial condition? I at 0 minus is equal to 0, and since this is a current through the inductance which cannot change instantaneously, I of 0 plus shall also be equal to 0. One initial condition, and the other is that Vc 0 minus is equal to V0 is equal to Vc 0 plus. Alright, this is the other initial condition. Now an integral differential equation, as I have told you, is always converted, it can be converted into a differential equation by one more differentiation. We want to get rid of the integral sign, so what I get is L d2i dt2 plus R di dt, and in the process d dt of V0 becomes equal to 0, and therefore we get simply I by C, which taken to the left hand side becomes 1 by C times I equal to 0. If you notice, this equation is also a homogeneous differential equation of the second order, and therefore this circuit is called a second order circuit, and we are indeed talking of natural response. The initial energy in this circuit comes from the capacitor voltage. It could also, instead of the capacitor voltage, it could also have come from an initial electromagnetic energy in the inductor. For example, the inductor could have a current of I0, and then at t equal to 0, it is connected across a capacitor and a resistor, exactly the same way, and we would have the same kind of differential equation, a second order differential equation, thus defining a second order circuit. Let us write this equation again. L d2i dt2 plus R di dt plus I by C equal to 0. I want to make a point regarding the initial conditions. Can you go back to the previous slide? Before I pass to the solution of the equation, you see, what am I going to do is to solve this differential equation for I. Alright, so I of t, and I of t I shall obtain in terms of unknown constants, which I shall try to evaluate from the initial conditions. One of the initial conditions is that I of 0 is equal to 0. I of 0 minus and 0 plus are the same. The other initial condition I said, it is not on I, it is on the capacitor voltage. Can we convert it to a condition on I? This is very illuminating by looking at this equation. Alright, let us consider t equal to 0 plus. At t equal to 0 plus, what is the value of I? It is 0. di dt is not 0, not necessarily. I can be 0, but it can be rising. So, and what about this integral? 0. And therefore, don't you see that my initial condition is L di dt at t equal to 0 should be equal to V naught, and therefore di dt at t equal to 0 should be equal to V naught by L. This is the other initial condition. So there are two initial conditions. It is a second order circuit. It stands to reason that you have to solve a second order differential equation, you require two initial conditions, alright, and the two initial conditions are that the initial current is 0 and that the initial rate of change of current is simply the initial voltage across the capacitor divided by the inductor. The resistance does not come into play anywhere in this. Why not? Because I of 0 is 0. So there is no drop in the resistance. Are these two initial conditions clear? Can we go ahead to the solution of the circuit? Once again we shall proceed from a physical reasoning rather than integrating directly physical or using an integrating factor as we do in mathematics. We don't want to lose sight of the physical situation, and so we say, all right, we notice that I di dt and d2i dt2 must be of the same functional form, otherwise their sum cannot be 0. If one is a sine, the other is a cosine, and the third is an exponential, obviously it cannot cancel, and therefore we argue once again that I must be of the form of a e to the st. A e to the st. Now if I substitute this here and clear a e to the st, a e to the st cannot be 0, clear a to the st, then what we will get is s squared L plus SR plus 1 over C shall be equal to 0. Do you see this? I have omitted a couple of algebraic steps. I simply substitute this, take 2 differentiation, I shall get S times R here and S squared times L. A e to the st I cancel because it cannot be equal to 0, and this equation, yes.
At time t is equal to 0 minus and 0 plus I is 0. So that implies that A is 0.
A is 0 at
And hence A into e to the square st is 0. You can't cancel it out.
that is at t equal to 0.
Yes, sir. So you have to apply that boundary.
Okay. All right. We shall apply that boundary condition later. All right. This is a first order. This is not a first order circuit, so this cannot be the complete solution. We are trying the form of the solution. We say, does this qualify as a form of the solution? Let me clarify this. In the first order circuit, we are trying a complete solution. We know the solution has to be of the form a e to the st. Here, obviously, since it's a second order circuit, the solution must be more complicated than a e to the st, because at t equal to 0, as you rightly pointed out, since I of 0 plus is equal to 0, a has to be identically equal to 0. So this cannot qualify as the total solution. But does this qualify as a form of the solution? This is what we wish to find out, and the physical situation will immediately bring in the total solution. As you see here, this equation S R by L plus 1 by LC equal to 0, this is a quadratic equation. So there are 2 values of S which satisfies the equation. There are 2 values of S. Originally it was only, in the first order circuit it was only 1 value of S. Here there are 2 values, and these 2 values are S1, 2. You know what this means. Subscript 1 comma 2, that we write both of them simultaneously. And you can see that this is minus R by 2L plus minus square root of R by 2L whole squared minus 1 over LC. There are 2 possible values of S, and therefore there are 2 possible solutions of the original differential equation, and these solutions are, my equation is L d2i dt2 plus R di dt plus I by C equal to 0, and the 2 solutions are minus r by 2l plus minus square root of r by 2l whole squared minus 1 over LC, and therefore the solutions are e to the s1t and e to the s2t. Both of them shall satisfy the original differential equation, and multiplying by any arbitrary constant will not affect the solution, and therefore we say these constants are, let us say, a1 and a2. Both of them individually satisfy the original differential equation, so the sum of them should also satisfy the original differential equation, and this qualifies as the general solution to the original differential equation. We shall not apply the initial conditions till we reach this point, till we get the general solution to the equation. A e to the st was a trial solution. We see that indeed it is of the correct form, but it does not satisfy the initial conditions. Therefore, why is it so? Because it is a second order circuit, and therefore there must be two linearly independent solutions. Is this phrase known to you? What does linear independence mean? That by multiplying this by a constant I cannot get the other solution. You see, e to the s2t cannot be obtained from e to the s1t by simply multiplying by a linear constant. Alright. These are two independent solutions, and now we can apply the initial conditions. The first initial condition is that I0 is equal to 0, that is a1 plus a2 should be equal to 0, which tells me that a1 should be equal to minus a2. Alright. In other words, the general solution therefore shall be of the form a1 e to the s1t minus e to the s2t. a2 is simply minus a1. And the other initial condition is that di dt at 0 should be equal to v0 by L, which means that a1, now make a ddt and put t equal to 0. ddt of e to the s1t is s1 e to the s1t, and if you put t equal to 0, then it is simply s1 minus similarly s2. Is that clear? I have omitted that differentiation step, and therefore a1 is equal to v0 by L s1 minus s2. Is that okay? Alright. And therefore my total solution I of t is equal to v0 by L s1 minus s2 times e to the s1t minus e to the s2t. This is the total solution. Total solution to the equation. Now, so far I have not said anything about the nature of these two quantities S1 and S2. If you recall, S1 and S2 are given by minus r by 2l plus minus square root of r by 2l whole squared minus 1 over LC. The nature of these two solutions, obviously these two constants obviously shall depend on the discriminant, that is d, which is r by 2l whole squared minus 1 over LC. If d is greater than 0, then obviously the two roots shall be real, distinct. Anything else that you can say? Negative. Isn't that right? Minus r by 2l plus a quantity which is less than r by 2l obviously shall be negative quantity. When the sign is negative, minus r by 2l minus, obviously the whole thing is negative. So all are distinct. These are real, distinct and negative. If d is equal to 0, obviously that is possible. By a combination of r, l and c, you could make them equal to 0. They are real, coincident, we don't say equal. They coincide, they coalesce upon each other, and they are still negative. Okay. If d is less than 0, these roots are complex. Why complex? Because there is a real part and d is less than 0, so this will be j times, okay, square root of minus 5 is j times square root of 5, where j is equal to square root of minus 1, alright. So you will have minus a real quantity plus minus j times another real quantity. So it will be complex, distinct, we can't say positive or negative, conjugate here. Suppose r is equal to 0, then the roots are not only complex, they are purely imaginary. They are purely imaginary because this is 0, square root of minus 1 over LC, so purely imaginary. To emphasize, you say purely, okay, purely imaginary, distinct and conjugate. We shall talk about this. Pardon me? They are of course conjugate.
So when d is 0, we will have different solution for the differential equation. Because we'll have to have two independent solutions, and when d is 0, S1 will be equal to S2.
In the case of repeated roots, as you know in the differential equation, we have to have a1 plus a2t multiplied by the exponential. But we will not bother about that. We will go by this and see what exactly comes from the physical picture. Alright, we will look at it from more a physical point of view, because it is introduction to electronic circuits that we are learning, not solution to differential equation. This is incidental. We have to solve the equation to be able to find a solution. Let us consider this case, d greater than 0. That is, roots are S1, S2 are real, distinct and negative, alright, and you already know that the current solution is equal to V0 by L S1 minus S2 e to the S1t minus e to the S2t. D greater than 0 means that R, L and C are such that this quantity R by 2L whole squared. Let us look at this is also interesting. D greater than 0 means what? That R by 2L whole squared should be greater than 1 by LC, which means that R should be greater than R square should be greater than 4L by C. Is that right? That is, R should be greater than 2L by C, square root of L by C. There are two things I want you to notice. That it depends on the total resistance in the circuit. Okay, if the total resistance in the circuit is large compared to, is greater than twice square root of L by C, well, the roots will be real and distinct. If you take a resistance, a rheostat for example in the circuit, and gradually reduce it, then you can see all the phenomena. That is, you can see real effect of real distinct negative roots, effect of real coincident negative roots, effect of complex roots, and effect of purely imaginary roots, if you simply go on adjusting this resistance. When it is 0, you will see completely imaginary roots and so on. Alright. The other thing that I want you to notice is that square root of L by C obviously has the dimension of resistance. Isn't that right? So if you wish to express the dimension of L in terms of the dimension of C and R squared, then obviously it would be this, right? L would be equal to CR squared. Now let us take a numerical example for this case. Let us suppose
What happens in circuit?
about what? How does the circuit behave? This is what I am going to show you. This is what I am going to show you with numerical examples. We have an example in which, let us say, L equals to 1 Henry, C equal to half farad, and R equal to 4 ohm. Alright. If this is the combination of the elements, then you see S12 is minus R by 2L, so it would be minus 2, is that okay? 4 divided by 2 into 1, minus 2, plus minus square root 4 minus 1 over LC. 1 over LC is, I have made a mistake. Let's take, would you pardon me, let's take C as 1/3 farad. I want to keep life simple, alright. Let's take C as 1/3 farad, then this will be 4 minus 3, which means that it is minus 2 plus minus 1. The roots are real, distinct and negative. So the roots are minus 1 and minus 3. And therefore I of t is equal to V0 by L is 1, S1 minus S2 is obviously 2, is that right? Minus 1 plus 3 minus 2, and then e to the minus t, S1 is minus 1 and S2 is minus 3, so e to the minus 3t. Okay, let me write it down again. I of t is equal to V0 by 2 e to the minus t minus e to the minus 3t. How do you think the current will behave with time? How shall it vary with time? Obviously at 0 minus the current was 0, at 0 plus the current will be 0. Put t equal to 0, it is 0. At infinity when t goes to infinity, this term goes to 0, this term goes to 0, 0 minus 0 is 0. So at infinity it must again be 0. Let me show infinity on a finite plane, okay, by a break. Let's say this is the point at infinity. So infinity is also 0. In between the current is positive, it doesn't change direction, it cannot be 0, and therefore it must have a maximum. It must have at least one maximum. In a higher order circuit it can have more maxima and minima, alright. So it must have at least one maximum. So it must go to a maximum and then goes to 0. We show a break because we are showing infinity on a finite plane, alright. So the current attains a maximum value somewhere, and one can, by differentiating this, find out at what value of time the current attains a maximum, and then what happens. One can also find out the total charge that is delivered to the circuit. What do you think will be the total charge? It will again be C times V naught, that is 1/3 V naught. If you integrate this from 0 to infinity, you shall get the same expression. On Monday we will consider the case of a complex root, that is d less than 0, and we will have fun, more fun there.